Hi everyone, I'm Jonas Verellen from the Soil Service of Belgium, and today I will represent my research about the interaction between soil moisture and nitrogen dynamics in the root zone of a conference pear orchard. First of all, I will introduce some important concepts which were used to carry out this research. The first important concept which was used is a nitrogen balance. This is a summation of all incoming and outgoing fluxes which determine the nitrogen content in the root zone of a pear orchard. Examples of incoming fluxes of nitrogen are, for example, nitrogen from atmospheric deposition, nitrogen from fertilization, and nitrogen from mineralization. Mineralization is a process by which organic matter is decomposed by microorganisms and mineral nitrogen is set free. Other processes which have a negative influence on the nitrogen concentration in the root zone are, for example, nitrogen denitrification, which is a conversion from nitrate to gaseous nitrogen forms like N2 or nitrous oxide, and nitrogen from which percolates from the root zone to the groundwater, for example. Since multiple nitrogen processes are dependent on the soil moisture content in the root zone, like for example, mineralization, denitrification, percolation, and nitrogen from capillary rise, the nitrogen balance is coupled to a soil-water balance. This soil-water balance works according to the same principle. It's also a summation of all incoming and outgoing fluxes, and processes which have, for example, an positive influence on the soil moisture content are precipitation and irrigation, and capillary rise from the groundwater table to the root zone. And processes which have a negative influence on the soil moisture content are, for example, water which leaches out from the root zone to the groundwater, and crop evapotranspiration by the pear tree. Also, water stress was measured in this research, and this was and for this, the stem water potential was measured, which is an indication for water stress. And the stem water potential is actually the pressure which a pear tree has to exert to suck up water from the root zone to the tree. The purpose of this investigation is to set up a mineral nitrogen balance to follow up the nitrogen cycle in the pear orchard. For this, soil samples from which the nitrogen content and soil moisture content was determined were taken. Also, the influence of water stress on nitrogen dynamics was determined by using the stem water potential, and spatial variability of drought and nitrogen dynamics was studied in 2 zones of the orchard. The impact of drought was also studied on phenological yield and fruit quality parameters, and also Sentinel-2 satellite data was used to see if the satellite data showed the same trends as the field observations. Finally, an answer will be formulated on the question whether commercial pear cultivation is possible on fertile pear orchards with limited nitrogen percolation, and also the potential of the mineral nitrogen balance will be discussed. So if the mineral nitrogen balance can simulate the nitrogen content in the root zone on a reliable way, it can be used to enhance fertilization decisions, which can possibly limit nitrogen percolation to ground and surface water. To show that this research is relevant, 2 graphs about the nitrate concentration in the ground and surface water in Flanders are given. And these 2 graphs show that water quality is deteriorating fast over the last years. So this shows that this research is really relevant. First of all, I'm going to spend some words about the orchard itself. It was located in central Belgium, near Brussels. It has 2 zones, Zone A and Zone B, with each 4 plots. And Zone A had a more silt loam soil texture, while Zone B had a more stony soil profile and a sand loam soil texture. Now the field data about stem water potential and water content will be discussed. And in the first graph, the stem water potential is shown. As you can see, the stem water potential was significantly lower during a large portion of the growing season in Zone B with a more stony soil profile and the sand loam soil texture. And also the gravimetric water content was significantly lower during a large portion of the growing season for zone B. So we can say that in zone B with the stony soil profile, there was a lot more water stress as compared to zone A. The NDVI, which is a vegetation index, was derived from Sentinel-2 satellite data, and a higher NDVI overall corresponds to a higher photosynthetic capacity and higher productivity of the pear tree. As you can see, the NDVI was significantly higher in zone A as compared to zone B. And as an example, an NDVI image is given here on the right, just before the harvest, mid-August. And as you can see, the difference in NDVI is really high between zone A and zone B. So again, we can say that zone B experienced more water stress, which can also be seen from this satellite data. Next, we can discuss some fruit quality, phenological, and yield parameters. For example, the starch score indicates that zone A has a significantly higher starch score as compared to zone B, which means that zone A had more ripe pears at harvest. Also, the shoot length was significantly higher at zone A as compared to zone B. And for example, the fruit set was also significantly higher, and at harvest, the yield was almost 10 kilograms per tree higher in zone A as compared to zone B, which indicates that the water stress in zone B is also reflected in the fruit quality, phenological, and yield parameters. Now the soil water balance will be discussed. As I said earlier, the soil water balance is summation of all incoming and outgoing fluxes, which determine the soil moisture content, like rain, irrigation, capillary rise, and deep percolation is subtracted also, like also the crop evapotranspiration. It was a very dry growing season with only 263 millimeters of precipitation, which is with only 146 millimeters of precipitation, which is only half of the normal value. But there was irrigated in the pear orchard. The groundwater table depth was located rather deep, so there was a limited opportunity for capillary rise from the groundwater table to the root zone. When the soil moisture content dropped below the critical soil moisture content, the stress function was used to adapt evapotranspiration. And when soil moisture content rose above field capacity, water was leached from the root zone to the groundwater. Also, the mineral nitrogen balance will be discussed. This balance consists of both chemical and physical processes. Chemical processes are denitrification and mineralization. Denitrification is calculated based on the potential denitrification rate, which is corrected for soil moisture and temperature and calculated on daily basis. And mineralization was calculated according to the mineralization rate. This mineralization rate was coming from an incubation experiment in a nearby pear orchard, which had the same soil texture, but since mineralization is largely dependent on carbon content, this mineralization rate of the other orchard was adapted for the carbon content in both zones of the orchard where this research was carried out. And mineralization was also calculated on daily basis and adapted for soil temperature and soil moisture. For the physical processes, for atmospherical deposition and fertilization, exact values were used. For nitrogen uptake by pear trees, an S-shaped curve was used, and for capillary rise and percolation of nitrogen, the soil water balance and the nitrate concentration of the groundwater was used. Now I will discuss the soil water balance. The soil water balance was calibrated in a way such that the simulations approximately follow the trends of the field data, and this was obtained when irrigation was scaled up with 45%. I will explain the soil water balance in more detail. The green line represents field capacity. So if the soil water content rises above the green line, water will percolate from the root zone to the groundwater. The red line is a water stress threshold. So if the water content drops below this red line, the pear tree will experience water stress. And as you can see nicely in these graphs, as you compare zone A with zone B, is that a longer period of water stress is simulated in zone B, which we could also see in the previous results and field observations. So the soil water balance corresponds with the previous observations and probably gives a realistic view about the soil water content in the orchards. For the mineral nitrogen balance, the nitrogen uptake in zone A was set higher as compared to zone B because like I already mentioned, in zone B there was a lot of water stress. So probably less nitrogen uptake could take place. As you can see in both graphs, the quality of the nitrogen balance is a lot worse for zone B as compared to zone A, but this has been caused by the high standard deviation of the field data, which make it hard to achieve a good fit between observations and simulations. For zone A, the quality of the nitrogen balance is rather good. As you can see, the simulations follow the trend of the field data quite well. And there must also be mentioned that the nitrogen content was higher at the start of the simulation period for zone B as compared to zone A. Now I will discuss the output from the nitrogen balance. It's important to mention that the nitrogen balance was set up for the herbicide strip. This is the strip in the pear orchards where the pear trees are planted and fertilization takes place. From the results of the nitrogen balance, we can see that mineralization in zone A was around 200 kilograms of nitrogen per hectare per year and only 150 kilograms for zone B. The higher mineralization in zone A has been caused by the higher carbon content in zone A, since mineralization is positively influenced by the carbon content. Mineralization was also a bit higher as compared to literature values, but in this research, mineralization was considered up to 40 centimeters depth, while in the previous research numbers from other parcels in Flanders, mineralization was only considered for the upper 15 or 30 centimeters. Denitrification values correspond nicely with literature values, but the nitrogen percolation values are really high, around 130 kilograms of nitrogen per hectare per year for zone A and 151 kilograms nitrogen per hectare per year for zone B. But there is to be mentioned that this nitrogen balance has been set up for the herbicide strip, and around half of the orchard consists of this herbicide strip. The other half consists of grass strips. And if we assume that no percolation happens in the grass strips because there is no fertilizations added over there, then we can assume that the global nitrogen percolation in the orchard is the percolation of the herbicide strip divided by 2, but still then the global nitrogen percolation in the orchard would be around 56 to 75 kilograms of nitrogen per hectare per year, which is still a high amount. Now I will discuss the influence of fertilization on the nitrogen percolation. Fertilization is necessary for fruit quality and yield, so it's difficult to reduce fertilization without reducing fruit quality and yield. The nitrogen input by mineralization was lots higher as compared to the nitrogen input by fertilization. So we can conclude that nitrogen percolation was inherently linked to fertile pear orchards with an optimal carbon content. There must also be mentioned that previous research has shown that fertigation and compost can limit nitrogen percolation, so this can be used to limit nitrogen percolation in the future. And now we can go over to the conclusions. Zone B with a lighter soil texture and the stonier soil profile was significantly drier and experienced more water stress. The nitrogen input by mineralization was lots higher as compared to the nitrogen input by fertilization. If we make the assumption that half of the orchard consists of herbicide strip where fertilization is added and nitrogen can percolate, and the other half of the orchard consists of grass strips where no fertilization is added and possibly there's only a limited amount of percolation, then the nitrogen percolation in the orchard would still be 56 to 75 kilograms of nitrogen per hectare per year, which is a relatively high amount of percolation. It's important to mention that different parameters were used to estimate the mineralization, so which brings uncertainty in the calculation. But from these results, we can say that the nitrogen balance can simulate the nitrogen content in the orchard in a reliable way, as we saw for zone A in the orchard. If these nitrogen balances are calibrated over a longer period with more field data, the predictions can become even better. So they can become a useful tool to enhance fertilization decisions and to limit nitrogen percolation to the groundwater. Commercial pear cultivation on fertile pear orchards with a high carbon content and limited nitrogen percolation seems improbable from this research, but further research is needed to confirm this. I want to thank you for your attention and do not hesitate to contact me if you have any questions. Thank you.